Hi students, today we'll talk about how to deal with the small samples when we uh, want to construct confidence interval of any given percentage. So let's start with the distribution that we are supposed to use, and when we say that we deal with small sample sizes, then it is n strictly less than 30. Population standard deviation is unknown. For this, we need to refer the previous lecture video where we have used this formula to construct 1 minus alpha percent confidence interval for the population mean mu. This is the case of the formula when we are given population standard deviation, which is sigma, is known, and a slight amendment is desired in the formula when we are not given population standard deviation. Instead, we make use of the sample standard deviation computed from the sample as a representative of the population standard deviation. This is the formula we apply when sigma is unknown. But when we are not given sigma anywhere in the question and n is less than 30, one more thing we need to make sure whether the sample data follow approx normal distribution. When the sample data follow approximately normal distribution, which is T, and we'll definitely talk about T distribution. But what amendments are desired in the formula, we need to first consider and focus on that. Instead of Z distribution, we are going to use T alpha by 2 or T distribution to estimate 1 minus alpha percent confidence interval. And since we have no information provided regarding population standard deviation in the question, we use again sample standard deviation in the formula to estimate population mean mu with an assumption that sample standard deviation is an approximated value of the population standard deviation. Now, what's the difference between the t distribution and the z distribution? As an example, I'm going to draw three different curves. As we have discussed and studied, in case of a sampling distribution, that as we increase our sample size, in that case, increasing sample size will make the curve steeper. So let's assume that this is the z distribution curve. Now, if we are going to draw t distribution curve that is relatively flatter, what I'm doing, I'm going to draw the curves of sample size 10 and sample size 20. So I'm using red color to draw the sample size of 10 curve. Here n equals to 10, and after changing the color, I'm going to draw another one with green. That will be roughly lie between Z curve and the sample size of 10 curve. Okay. Now you can see if we compare this relative steepness of the three curves, we can notice one thing, that the sample size of 10 curve is the flattest among all three. Then sample size of 20 is relatively steeper, and samples and then Z distribution is the steepest among all three. So we have taken notice of this thing, that when we increase our sample size, the curve gets steeper. And if we deal with smaller sample size, we observe greater degree of variability in flatter curve due to the smaller sample size. And in case of a greater sample size relatively, that is, if we compare with 10, the sample size of 20 curve, then we expect sample size of 20 curve relatively steeper, and it will contain less degree of variability. As far as the common characteristic of Z and T distributions are concerned, both have the zero value in the center. T and Z both have negative values on the left part of 0, and both T and Z have the positive values located above 0 value. So in this manner, both T and Z distribution have a similar characteristic. Now, just have a look on the T table and we will try to compare the similarities and differences between the Z and T table. Now, that's the T table. The very first column contains the heading of degrees of freedom. DF stands for the degrees of freedom, and degrees of freedom is in fact the divisor of the sample standard deviation. The difference between the sample standard deviation formula and the population standard deviation formula is population standard deviation has this formula. This is what we have used already in case when we have dealt with the sampling distribution. Similarly, the sample standard deviation has the formula not mu but x bar, and then divided by n minus 1. This n minus 1 factor or divisor we call the degrees of freedom and denoted as df. This is what you can identify as the heading of the first column of the T table. Now, if we compare it with the Z table, we have noticed that the probabilities are given inside the Z table, but if we compare these numbers which are given inside the T table, these numbers can never be the probabilities because these are all greater than 1. So these are in fact the T values. So this is the point of reference between the structure of Z table and T table. In Z table, Z values are given outside the table, whereas probabilities are given inside the table. Over here, T values are given inside the table. These are all the T values associated with a particular degrees of freedom. And degrees of freedom, I have already told you that it has a formula n minus 1. Now, if we notice the headers of these 5 columns, these subscripts are indicating certain confidence interval related t values. Now just recall, how do we construct or how do we determine z values for 90 for 80% CI. So for 80% CI, what we need to do, we need to consider the central 80% part under the curve. This is how we are left with remaining 20% that should be equally divided to both the tail and regions. And this is in fact the representation of Z for 80% CI. Now, at the time of derivation, I've written down this as minus the alpha by 2 because alpha by 2 has the value 10% here. Alpha by 2 has the value 10% here. So this borderline we can indicate as minus Z with the probability associated with this particular borderline, that is area below this. And this 0.10 will indicate the area above this borderline with plus sign. So same thing if you would like to connect. So the areas we need to consider that we have assigned in each tail, it's of 10%. So now if we consider the header of the first column or subscript of a first column of t value or t table, this is t with subscript 0.10 and it indicates that this is the t value or these are the t values, all available t values in this column are the t values corresponding to 80% CI. Similarly, if we consider central 90% area under the curve, which is referring the 90% CI, so central 90%, if we take, so remaining 10% we equally divide to two tail and regions, and this is how we get 0.05 or 5% area in each tail. So this is what this is representing the t values or set of t values corresponding to 90% confidence interval. Now move to the next column. It does contain the subscript of 0.025. So it is in fact 95% because in case of 95% confidence interval we allocate or assign the 95% probability in the center, and then remaining 5% will be equally divided to two tail and regions, and this is how we get 0.025 in each tail. Therefore, all the t values given in this column are representing 95% CI related values. Similarly, if we consider this column, this has a subscript 0.01, and how do we get this 0.01 in each tail? When we consider 98% confidence interval, which is the central part under the curve. So when we take 98% confidence interval in the central area, then remaining 2% will be equally assigned to two tail and regions. Each tail will contain 0.01. Similarly, 99% CI, for 99% CI, we take remaining 1% to be divided into two tail and regions, and this is how we get the probability of 0.005 in each tail. So these column will give you all related values to the 99% CI. So this is how we read out the values from the T table. Let's start with, if we are given 11 observations in a data set and we are asked to construct 95% CI, so what value of T we need to consider? So we go to 11 minus 1, that is 10th row, and since the middlemost column is representing 95% CI related t value. So the value would be 2.228. This is how we do it. Now, if we go to the assumption that I have written on the previous page, or the conditions under which we apply or use t distribution, n is less than 30, sigma is unknown, and data are approximable. So the first two conditions, we can identify whether these two conditions are matching or not by just looking at the question. If we consider the question and if we find over there that the total number of observations given as a sample size are less than 30, so it will be indicated over there. Similarly, sigma, we look for in the question. If sigma is not provided, so sigma is unknown. Similarly, the third condition, data are approximable. So to check the third condition, whether it exists or not in case of a given sample data, we draw a graph that we call normal probability plot. To draw normal probability plot, we need to establish a connect between our data values and a variable that we call normal scores. From where do we get normal scores? So I am going to introduce a table that we call normal scores table. Now we are going to discuss normal scores. If we look at the column number 5, 7, 9, 11, 13, mean to say that all odd ordered columns. So in case of odd ordered number of observations, if we are given, we can determine the middlemost number. And z value that lies in the center under the curve is 0. All the values that are located below z is equal to 0 or below center are negative. All the values above center are positive. So if we try to allocate under the standard normal curve 5 observations given in the data, the ideal normal scores that they should have are 0 in the center. The two values below 0 must be negative. The two values above 0 must be positive. And you can take notice of one thing, that the first value is similar to the last one. The second value is same as the second last. And middlemost is 0. Same trend you can observe over here. Centermost value in case of 7 number of observations is 0. The two neighborhood values are same but opposite in sign. The other two neighborhood values are again same but opposite in sign, and the other two, or the last two, that is the first one and the last one, are exactly the same but opposite in sign. So you can take notice of the same thing in all odd ordered columns. Now we know when we are given even number of observations in a data, so we cannot determine the middlemost number. Therefore, none of the observations will be 0, or centralmost number we cannot identify. Therefore, we cannot find any 0 value as a centermost value in 6th, 8th, 10th, 12th, 14th, and so on. So you can see in that case, if we are given 6 observations in the data, their corresponding normal scores will be, half of them will be negative and half of them will be positive, and this is what you can take notice of. And these values are again symmetrically distributed. First three values are negative, next three values are positive, and these are moving away from 0 to the left, and these three are moving away from 0 to the right under the normal curve. So 8. If we consider 8 observations, we can find out the same thing. 4 are negative, 4 are positive. In 10, in case of 10 observation, 5 are negative, 5 are positive. In case of 12 number of observations, 6 are negative, 6 are positive. So since in every column of this table, all the values are symmetrically distributed, same in values, but opposite in signs, when we add the normal scores given in each column, their sum would be 0. Add them all, you can get 0. Adding them all, you can get 0. Adding them all, you can get 0, and so on. So sum of all columns given in this table is 0. Now, if you would like to establish a connection between our data values and the normal scores, drawing a graph or scatter diagram is the best way. And when we draw scatter diagram to observe a relationship between two variables, so we can have three different possibilities. On x-axis, on horizontal axis, we have to take our data values, and on vertical axis, we have to take normal scores. Normal scores are denoted with the alphabet W. This axis is for positive normal scores. 0 is located here, and this region or zone is for negative Z values or normal scores. So when we connect our data values with the normal scores and we spot this trend, this we can call perfect linear. So this data is indicating perfect linear behavior. Therefore, our conclusion would be the data are perfect normal. And perfect normal means Z can be used. Another possibility, maybe instead of getting exact or perfect linear, we may get this sort of graph. And this is not exactly linear, but approximately linear. And approximately linear means approximately normal. Why? Because we are establishing a connection between two variables. One is our data values, another is normal scores. So approximately normal means t distribution can be used. There is another possibility. This is a non-linear behavior, and this is formulating a curve. So non-linear, if we end up with, does indicate we can draw a conclusion that the data do not follow normal or the data are non-normally distributed. Over here you can observe that I have drawn all three data sets as a positively related data sets. Why this so? Because this is the norm, that since we are going to establish one-to-one correspondence between our data values and the normal scores, and since normal scores are arranged in ascending order in the table for all given number of observations, therefore we are bound to arrange data in ascending order at the first place. Then we can draw this graph. So I'm taking a data as an example. Let's assume that these are the wages data of the wages of 10 workers working at a construction site. And this may be, let's suppose, 30, 25, 20, 40, 45, 42, 50, 60, 52, and 45. So I have taken as an example the wages of 10 workers. Now what we need to do, we need to first arrange this data in ascending order. And for this purpose, we need to take help from stem and leaf display. What is stem and leaf display? A way to organize the data, and it is also the way to arrange the data in ascending order. Now stem means we need to first identify the minimum value in the data, which is 20, and the maximum is 60. What we do, we will introduce the stem of 20s, 30s, 40s, 50s, and 60s over here. And we start tallying the numbers as these are given in the data. So first observation is 30. So 0 of 30 I will copy here, and we read it, we define a key as 3 with 0 is equal to 30. So when we read a number, we read it jointly. So 25, 20, 40, 45, 42, 50, 0 of 60, again 52, sorry, again 52, and then for 45 here, we can tell you. Now, we need to copy this again, and we rewrite down numbers in each stem in ascending order. That's 2, 0 should be written down first, and then 5. No problem that in the second stem, because it is only one observation it has. Then 0, 2, 5, 5. Then we have 0, 2, that is already arranged, and 6, 0, that's already arranged. Now what we do, we need to copy the data in this way. Now we need to write down the numbers in ascending order as 20, 25, 30, 40, 42, 45 twice. Then we have 50, 52, and then 60. Now what we do, we copy down the normal scores as per the number of observations, which is 10 over here in our case. So we go to the normal scores table. We choose the normal scores provided in the 10th column, because we are given 10 observations in the data, starting with minus 1.55, minus 1, minus 0.65. So minus 1.55, minus 1.00, minus 0.65. We copy the other two as well. That's minus 0.37 and minus 0.12. So minus 0.37 and minus 0.12. Similarly, that's 0.12, 0.37, 0.65, point, this is 1.00, and then 1.55. Now what we do, we will draw a graph. On vertical axis, we take normal scores. On horizontal axis, we take our data values. So when our data does not start from zero value, we take a pause on the graph and then we start from the very first value. So let's take this as 20, 25, 30, 35, 40, 45, 50, 55, and 60. Okay, now minimum value is minus 1.55, maximum value is 1.55. So we scale our vertical axis as 0.2, 0.4, 0.6, 0.8, 1.0, 1.2, 1.4, and 1.6. Similarly, below zero value, that's minus 0.2, then minus 0.4, then minus 0.6, then minus 0.8, then minus 1, then minus 1.2, then minus 1.4, and then minus 1.6. Now read out the value on horizontal axis and locate accordingly its corresponding normal score. So 20 with minus 1.55, that may be located here roughly. Then across 25, that's minus 1. Then across 30, it is minus 0.65, nearly over here. Then across 40, that's minus 0.37, roughly here. Then across 42, we have minus 0.12. That's over here. Then we have no 0.12 at 45 here. Then we have at 50, at 45 again, another value 0.37 here. Then across 50, it is 65. 50, it is 0.65, sorry. Then across 52, that's 1 here. Then across 52, 60, this is the very last value at 1.55. So what we can observe easily, that this is approximately linear behavior. Approximately linear. Now what we do, we will compute the mean value. So if approximately linear is the trend that we have spotted on the basis of this normal probability plot, it can be concluded that the data follow approx normal behavior that we were looking for, and t distribution can be used to estimate confidence interval. So what we need to do, we need to enter the values in the software or in the calculator, and from there you can get the mean and standard deviation computed from there. So what I'm going to do, I'm going to enter the data and compute mean and standard deviation using Google. Mean and standard deviation calculator. So what I would do, we have 10 values, 20, 25, then we have 30, 40, 42. We can alternatively use Excel as well, but in your case you are bound to use your calculators because in the exam you have to use it. Then after 45 we have 50, 52 and 60.